Neutralization reactions. Okay, these are actually just double displacement reactions with an acid and a base where we get water as a product. Okay, so we get something like this. So we've got some sort of acid reacting with a base, okay, and we get water and some sort of salt. And then if we heat that solution, remember that triangle, heat, okay, if we heat that solution and get rid of the water, then we're left with the resulting salt. So when we look at these, we can actually figure out three different types of equations. We're going to write what we call a net ionic equation. The net ionic equation is nothing more than just what actually reacts. Because remember, when we have these aqueous solutions, things disassociate into solution. When they are in solution, they stay as dissociated ions, not as a product. So let's figure out what actually we're forming. Now, occasionally we can do an acid-base reaction where we end up with some sort of insoluble compound. Most of the times, though, we end up with a soluble salt. So let's take a look at this reaction right here, barium hydroxide and oxalic acid. So to start off with, we're going to write the normal equation that we usually write. So barium hydroxide okay, so there's our barium hydroxide, and oxalic acid. All right. All right, and then we're going to get barium oxalate and liquid water. Because anytime I have H plus and OH minus, I form water. Okay, we need to balance it, and so when we balance it, we get a 2 right there. Okay, now what we're going to write next is what we call the total ionic equation. The total ionic equation is going to take into account every single ion, including ones that are spectators and just hang out, okay? So what we call an ion that doesn't actually do anything in a reaction is a spectator ion. It starts off as an ion in solution, and when all is said and done, it's still an ion in solution. It didn't do anything. It just kind of hung out there. All right, so our barium hydroxide, okay, we have this Ba and that OH with a 2 there. So barium, okay. Okay, and then that OH with the subscript 2 means I have 2 hydroxides. So I have 2 hydroxide. Okay. My oxalic acid, I have that H2, so I have 2. So oxalic acid is a diprotic acid. And then my oxalate. Okay. All right, and then my barium oxalate is an aqueous product, so we keep that in solution. There's the oxalate anion. I'm gonna run out of room, so I'll write that on the bottom there. Okay, so now let's take a look at this. When I look at my reactants and my products, I have to assess what reacted and what was a spectator. So if I look at my reactant side, I have a barium ion. If I look at my product side, I still have a barium ion. Barium was a spectator. It didn't do anything. Okay? Now, if I look at my reactant side, I have a hydroxide ion. If I look at my product side, I no longer have a hydroxide ion. So I'm going to highlight the hydroxide there. Okay? My reactant side, I have 2 H plus ions. I don't have those on my product side. I'll highlight them. My reactant side, I have an oxalate anion. Product side, I still have that oxalate anion. And then on my product side, I have these waters that didn't show up on my reactant side, so I'll highlight those. So what I've highlighted are the things that actually reacted. I had 2 H plus ions and 2 hydroxide ions come together to give us 2 waters. Okay, so we'll start off here. All right, Now, when we think about the net ionic equation, and we look at what just reacted, if I look at this here, I have a 2 in front of everything, so I can reduce this down. So this is going to reduce down to the net reaction here was a proton. That got really messy. Sometimes trying to write at the very bottom of my iPad, I don't have a good place for my finger to rest, or my hand to rest, and so it gets a little funky. All right, so I have my H+, I have my hydroxide, and I get, so our net ionic equation, our net reaction when we do an acid-base neutralization, the vast majority of the time is just hydrogen ion plus hydroxide ion gives us water. Again, every once in a while, we can do a reaction where instead of something like this barium oxalate, which is soluble, we end up with an insoluble salt. And so then our net ionic equation would include everything. But for the vast majority of the time, it works out such that our resulting product is some sort of soluble aqueous salt and water. So our net reaction is simply the formation of water. Okay? Now, when we do these acid-base neutralization reactions, we're usually doing what's called a titration, where we start off with usually a known amount of something, either the acid or the base. And our goal is to figure out which one we don't know. And so we run the titration and we figure out either the concentration of the base solution or we figure out the concentration of some sort of acid solution we started off with. And so we run these till we get to the equivalence point. The equivalence point is when the reaction stops, and it's when the moles of acid equals the moles of base, when we've got that stoichiometric equivalence there. Okay, and so a good portion of these, especially at a basic teaching lab level, is we use what's called phenolphthalein. Phenolphthalein is a really good indicator. It starts off colorless in an acidic or a neutral solution, and then at the equivalence point of these types of titrations, we end up getting this faint pink color. Because when we think about neutralization reactions, here's the thing. Our final solution is not necessarily a pH 7 neutral solution. Sometimes our final solution is acidic. Sometimes our final solution is basic. Even though we've reacted all of our starting acid and base, the ions floating around in solution interact with the water. And that interaction with the water sometimes ends up giving us an acidic solution and sometimes ends up giving us a basic solution. It just depends on what we do. So we use this phenolphthalein indicator for a lot of stuff. So of course, now we're going to practice some math. All right. So I've got a sample of phosphoric acid. Did a titration with potassium hydroxide. I want to know what the concentration of that original phosphoric acid solution was. So when we have a problem like this, the first thing we have to do is write and then balance our equation. So let's go ahead and do that. So phosphoric acid is a triprotic acid, so there's 3 hydrogens on there. We get H3PO4. Okay, potassium hydroxide. All right, so we'll do our double displacement reaction. We're going to get potassium phosphate and water. Okay? We have to balance this. Our balance is we end up with 3 potassium hydroxides and 3 waters. Okay? So we want to know what that concentration of the phosphoric acid was. So I'm going to switch slides so I have a blank slate. Okay, so when we do this, we're just doing stoichiometry with a solution. So in order to do stoichiometry, I have to get moles, right? So if I have a volume and I have a concentration, I can calculate moles. All right, so what we're going to do is we are going to go from volume of our potassium hydroxide to moles. Okay, from moles potassium hydroxide to moles phosphoric acid, and then from moles of phosphoric acid to molarity. Okay? All right, so let's start this. So we have 37.29 milliliters of our potassium hydroxide. Now remember, molarity is in moles per liter. Okay, remember, molarity is moles per liter. So in order to use the molarity to figure out moles, I need to convert this from milliliters to liters. So I have 1 liter in 1,000 milliliters. Okay, the concentration of our potassium hydroxide was 0.5277 molar, so I have 0.5277 moles of potassium hydroxide in every 1 liter of that potassium hydroxide solution. Okay, my balanced equation tells me that I have 1 mole phosphoric acid for every 3 moles of potassium hydroxide. Okay, now if I stop there, I will have moles. But what I'm trying to get to is moles per liter. So what we were told initially is we had a 50 milliliter aliquot of our phosphoric acid. So to get molarity, we need to convert to liters. So 50 milliliters, we'll get a liter for every 1,000 milliliters, and so we'll get 0.05 liters. So what I'm going to do now is I'm going to add one more step onto this. I'm going to put a unitless 1 here over my 0.05 liters. And I'm going to show you in just a second. This gives us molarity. So our milliliters for my potassium hydroxide cancel out. The liters cancel out. The moles cancel out. Okay? And then what I have on top is moles, and what I have on bottom is liters. So I have moles over liters, which is our molarity. So I can do this all in one long calculation. And what's nice about this is now I don't have to stop and try to round anything off and accidentally potentially introduce a rounding error or a transposition error into my calculation. I can do all of this all at once. And so what I'm going to get is 0.1312 molar phosphoric acid. Okay, and we have 4 sig figs because I have 4 here, I have 4 here, and I still have 4 there. Okay, so that is how we deal with that. All right, we can also do these when we start off with grams. So sometimes when we're doing these titrations, what we have to do is we have to do what is called a standardization, or sometimes we're just kind of getting a ballpark idea of how much of a solution we need. So in this case, we've weighed out some oxalic acid. We're going to dissolve it in water. And then we want to figure out, if I want to neutralize this oxalic acid, how many milliliters of the sodium hydroxide do I need in order to complete the reaction? So once again, to start off with, we have to write an equation and then balance it. So sodium hydroxide, okay, and that oxalic acid we just looked at. Okay, and we get sodium oxalate and water. Okay, we need to balance this, and we'll get 2 and 2. Okay, I'm going to give myself a little more room to write, so I'm going to switch over here.